Dear students, in this session I am going to discuss Abbe's sign condition and Smith-Helmholtz equation from geometrical optics. So why do I require the study of these conditions means next in the same session I am going to discuss about the aplanatic surface. Okay, so in order to define an aplanatic surface, so the rays will obey the aplanatic points and surface condition only when they satisfy the Abbe's sign condition, okay, as well as the Smith-Helmholtz equation. Okay, for that case we are going to study the Abbe sign condition as well as Smith-Helmholtz equation. Okay, now we will derive the Abbe sign condition. Okay, so here step by step I am going to show how we are going to draw the ray diagram in this case. Okay, so this is the common principal axis, horizontal line with respect to this spherical surface xy, and this is what I have considered an object. Here object is an extended object, it's not a point object, and this object is placed perpendicular to the common principal axis having certain height. Okay, next this is one incident ray which is made to pass from the object on the and made to incident on the spherical surface. After refraction, this is what the refracted ray, and this refracted ray will meet the common principal axis at this particular point. So this is another one incident ray which is made to incident in the direction of center of curvature. This is what the center of curvature. So hence without deviation the refraction occurs here, and finally we get the real and inverted image at this particular position. Is it clear? Okay. Here AB is a linear object as I told you, and A dash B dash is it's a linear inverted image. H1 is the height of the object and H2 is the height of the image. Right? H1 and H2 are the heights of the object and image respectively. So this dotted line indicates the normal. So this normal is drawn from the point of incidence passing through the point of incidence as well as the center of curvature. Hence it is a normal to this spherical surface xy. This is the angle made by the incident ray with the normal, and it is considered as an angle of incidence. And here it is the angle made by the refracted ray with respect to the normal, hence it is considered as the angle of refraction. This is the angle made by the incident ray with the common principal axis, and it is going to be denoted by θ1, and this is the angle made by the refracted ray with the common principal axis, that is going to be taken as θ2. Okay, next again AB the object, xy the spherical surface, I the angle of incidence, P the pole or vertex of the spherical surface, C the center of curvature, Q is the point of incidence, A dash B dash is nothing but the height of the image, and F2 is the focal length of the spherical surface xy. Okay, so now we will derive the expression for Abbe's sign condition. So in figure I represents, as I told you, the angle of incidence, R the angle of refraction. So now here I am going to take the two ratios. Okay, that is sin I by sin θ1 is equal to AC divided by QC. Okay, and sin R divided by sin θ2 is equal to CA divided by QC. So this can be obtained. So the opposite side of I is nothing but AC, opposite side of θ1 is nothing but QC. If you refer the figure, so the side of the angle of incidence is directly proportional to the sine rule, that is the opposite side AC. By referring to that theorem, this ratio is going to be written here. In the same way, sin R is equal to sin R divided by sin θ2 is equal to the opposite side of angle R is nothing but a CA dash, and the opposite side of angle θ2 is nothing but a QC. So if I take the ratio sin I by sin θ1 divided by sin R by sin θ2, I will get this particular equation, that is sin I divided by sin r is equal to AC divided by CA dash into sin theta 1 divided by sin theta 2, right? Again, from Snell's law we have the relation mu1 sin I is equal to mu2 sin r. Therefore, the above equation can be written as a mu1 sin I by sin r can be replaced by mu2 divided by mu1. So therefore the equation becomes mu1 AC sin theta 1 is equal to mu2 CA dash sin theta 2. Now if you consider the triangles ABC and A dash B dash C from the figure, right? So these two triangles appears to be similar. So by using the similar triangle theorem, I can write the CA dash divided by AC is equal to A dash B dash divided by AB, where A dash B dash is nothing but H2 and AB is H1. So CA dash divided by AC can be represented by H2 divided by H1. So in this equation, CA dash is going to be replaced by H2 and AC is going to be replaced by H1. So here it is. Now instead of those two, I have replaced by H1 and H2. So therefore mu1 H1 sin theta 1 is equal to mu2 H2 sin theta 2, and this condition is known as a Abbe's sign condition. Dear students, I tell you that this may appear for the point of examination for 5 marks. Here there are certain things which has to be noted here. So the Abbe's sign condition is generally used in calculating the resolving power of the microscope, and this condition is applicable even when the rays are not paraxial. Okay, so it is applicable to any system of refracting surface. It may be a concave as well as a convex. Yes students, so Abbe's sign condition is given by mu1 H1 sin theta 1 is equal to mu2 H2 sin theta 2. By using the same figure, we are going to arrive one more relation, that is the Smith-Helmholtz equation. Okay, so again by referring to the figure 1.6, the angular magnification, this is the standard definition, that is angular magnification is given by alpha is equal to tan theta 2 divided by tan theta 1. Or if I take the value of tan theta 2 and then tan theta 1 from the figure, I can write alpha is equal to QP divided by V and AP divided by U. So finally I will get it as U divided by V. U divided by V. Now this U divided by V is nothing but alpha means U divided by V. Alpha is equal to U divided by V means alpha is again tan theta 2 divided by tan theta 1. So therefore I can write it as U by V is equal to tan theta 2 divided by tan theta 1, and I will take this as equation 1. So now the linear magnification is given by M, and it is given as the ratio of height of the image to the height of the object. So H2 divided by H1. Okay, so which can be written as mu1 by mu2 into V divided by U. Mu1 by mu2 into V divided by U. Next, this H2 divided by H1 into V divided by U is equal to mu1 divided by mu2. I can write it like this. Or I can also write it as H2 divided by H1, where I will replace U by V by tan theta 2 divided by tan theta 1, again which is equal to mu1 by mu2. So therefore this is going to be considered as equation 2. Okay, so thus I can now I can calculate the product of linear magnification into angular magnification. Here I have equation from in equation 2 I equated linear magnification, in equation 1 I calculated the angular magnification. So now I am going to take the product of these two. Okay, so linear magnification into angular magnification is found to be equal to mu1 divided by mu2. If I multiply that, I will get that equation. So therefore mu1 h1, and finally I can write it as mu1 h1 tan theta 1 is equal to mu2 h2 tan theta 2. So this is known as a Smith-Helmholtz equation. Further, for in case of paraxial rays, again theta 1 being a very small, okay, so tan theta 1 can be approximated as a theta 1 only. Okay, and tan theta 2 is also approximated to be theta 2 only. So therefore the above relation can also be expressed as mu1 h1 theta 1 is equal to mu2 h2 theta 2 by avoiding tan here. Okay, so this is an assumption. So this can be considered as equation 3, and this is known as a Lagrange's law. So above equation mu1 h1 tan theta 1 is equal to mu2 h2 tan theta 2 is known as a Smith-Helmholtz equation, and in case of paraxial rays, since theta 1 is practically very small, so therefore tan theta 1 can be approximated to be theta 1 and tan theta 2 can be approximated to be theta 2. So this is Smith-Helmholtz after approximation. So it can be written as mu1 h1 theta 1 is equal to mu2 h2 theta 2, which is known as a Lagrange's law. So dear students, in this session, okay, we have seen or we have learned how to obtain an expression for Abbe sign condition and how to obtain an expression for Smith-Helmholtz equation. Now I will switch on to another one point, that is aplanatic point and aplanatic surface in my next video. So I hope now you are clear with deriving the aplanatic point, deriving the Abbe sign condition as well as the Smith-Helmholtz equation. Right? Now I will go for the aplanatic points and surfaces. So only we have a qualitative discussion in this case. So I will discuss it in a brief way. Okay. So what are aplanatic points and what are aplanatic surface? A spherical refracting surface. See here, always there is a problem whenever we come across the refraction of light with respect to a spherical surface. A spherical surface forms the image of a point object as a point only in case of paraxial rays. So when this condition is not satisfied, the refracted rays will not have a common point of intersection. It means the image of an axial point object will not be a point image. So the departure from the ideal point image is going to be termed as a spherical aberration. I repeat once again. So spherical aberration is going to come in case of the spherical surfaces. So the spherical aberration, because of spherical aberration, what happens? We are unable to get the image of a point object as an image, because all the refracted rays are not going to have a common point of intersection. Okay, so that is what the difficulty. So in order to overcome this effect, we are going to define aplanatic surface as well as aplanatic points. Okay, so first I will define an aplanatic points. Okay, so aplanatic points are nothing but the 2 points on the axis of an optical system having the property that the rays proceeding from one of them will all converge to or seems to diverge from the other if the rays fulfill the Abbe sign condition. So here, that is what we require the study of Abbe sign condition. Okay, I repeat it once again. So let me consider here, this is a spherical surface. Okay, so in this spherical surface we have 2 points S1 and S2. So this spherical surface, I can term it as an aplanatic spherical surface, provided when the rays originating from S1 after suffering reflection and reflection, they have to meet at a common point S2. Okay, so then only it can be considered as these 2 points S1 and S2 can be considered as aplanatic points. So therefore, this is what the simple example. Here I have written the 2 foci of an ellipsoid of revolution are an example for aplanatic points, right? So now we will go for aplanatic surface. So aplanatic surface is a spherical surface or an optical surface in which every point on the surface for every point on the surface, the sum of the optical distances to two fixed points in a space has a constant value. So this is what the basic condition for a spherical surface to be an aplanatic. It means, I repeat once again, it is a spherical surface in which for every point on the surface, okay, the sum of the optical distances to two fixed points. Okay, if you consider two fixed points, so sum of their optical distances to these two fixed points in a space is going to have a constant value. And one more thing is, the surface does not contribute spherical aberration, coma or astigmatism to the image. So these are nothing but the aberrations related to the spherical surface, which you are going to learn in our further discussion. So spherical aberration, as I told you, that it is because of spherical surface the rays are unable to meet at a common point of intersection on the principal axis. So this surface, when I define the surface to be aplanatic surface, if it satisfies this condition that for every point on the surface, okay, the sum of the optical distances to two fixed points in a space should have a constant value. If the spherical surface satisfies this condition, so then it is not going to possess any spherical aberration and the surface is going to be considered as an aplanatic surface, right? Or in general, we can define this aplanatic surface as an aplanatic surface is characterized by the property of forming a point image of a point object placed on the common principal axis. It means, if the surface satisfies this condition and behaves like an aplanatic surface, then this aplanatic surface will be able to form the image of a point object as a point image. Okay, so for your knowledge, here with a ray diagram I have shown you the aplanatic points as well as a surface. So in this figure we have an object at this particular point, right? O is an object, C is the center of curvature and I is the point image. Okay, now the ray of light is made to incident along OA. Okay, so it gets refracted along AB. So CN is the normal drawn to the surface, and this refracted ray, when it is produced backwards, okay, it will meet the common principal axis at a point I, where it is going to form the point image. So O is the object point and I is the image point, which is a virtual image. So with this figure, I can say that the image and object points are known as aplanatic points or foci of this particular spherical surface, because the ray of light which is coming from O, right, after refraction seems to diverge from this particular point I, right? So either it has to meet that particular point I in case of formation of a real image. Since here we are going to get the formation of a virtual image, so here the refracted ray appears to diverge from this point I. Okay, hence they have satisfied the condition. The light coming from one point after suffering reflection and refraction, okay, it should meet another point or appears to diverge from that point. So in our case, it appears to diverge from this particular point. So this refracted AB appears to come from the point I. Getting my point? So that's why this refracted ray is said to be diverging from the point I. So therefore, in this case, O and I are going to be considered as an aplanatic points, and this spherical surface is said to be an aplanatic spherical surface. Okay. In further discussion, okay, if you want to go for further applications of these aplanatic points and surfaces, but it is not there for your syllabus, we are going to prove that the distance of this object from the center of curvature is r divided by mu, and distance of the image I from the center of curvature as a mu r. Okay, this can also be proved, but it is not necessary here. So just it has to be discussed qualitatively. So I tried to convince you what are the aplanatic points and the surfaces, because in order to avoid the aberration, because whenever we come across the refraction at spherical surfaces, this aberration is the main problem due to which you won't get the clarity in the formation of the image. But today we have so many optical instruments where we are going to get a clear image. Okay, so all these things are possible with the application of these aplanatic points and the surfaces. In your higher studies, again you will come across this aplanatic points and surfaces, and you may derive this distance of the object from C to O as r by mu, and from C to I as a mu r. But in our case, it is just sufficient to know what are aplanatic points and surfaces. Dear student, I hope now you are clear with the definition of aplanatic points and surface. Thank you very much.